Could we really create an international antimatter delivery service? Discussions of antimatter are regularly confined to the realms of science fiction. Antimatter fuels futuristic starships, is a highly sought after power source, or is the key to producing the most destructive weapons imaginable. However, although antimatter may frequently appear in fictional contexts, studying its properties in the real world could be the key to understanding why we're even here to ask any questions at all. Despite the importance of interrogating the properties of antimatter, the only places on Earth where such material can be created, captured, stored and studied efficiently are enormous, powerful and expensive particle colliders, facilities that few laboratories have access to. Indeed, CERN's appropriately named Antimatter Factory is currently the only place on the planet where scientists can store and study antiprotons, the mirrored antimatter version of the proton, a particle that makes up part of every atomic nucleus we encounter. This is an unacceptable situation that scientists from the baryon-antibaryon symmetry experiment, or BASE collaboration at CERN, wish to rectify. The BASE experiment at CERN is a stationary electromagnetic particle trap fully integrated into CERN's Antimatter Factory, and has conducted some of the world's most precise measurements of the properties of antiprotons. However, they want to go further. They want to expand beyond CERN and pioneer the transport and delivery of antiprotons to far-flung experimental facilities lacking their own antimatter-producing colliders. 2 weeks ago, BASE scientists tested a sub-project of the main BASE experiment, an apparatus known as BASE STEP, a portable electromagnetic particle trap. BASE scientists showed that portable trap is capable of stably storing and transporting free, unbound particles from their point of production at CERN via road to a remote location. The shipping and receiving of antimatter could soon be a reality. Antimatter could be shipped from central production facilities, such as the colliders at CERN in Geneva, along Europe's highways and autobahns, to laboratories across Europe conducting precision antimatter measurements. Although this might invoke images from Dan Brown novels and the creation of destructive antimatter devices, such concerns are misplaced. Given the small numbers of particles involved, we are unlikely to see explosions of destruction, but rather explosions in collaboration, cooperation, and our understanding of antimatter, nuclear structure, and potentially the origins of our universe. Today we will come to understand how antiprotons are created, stored, and studied, and exactly how and why a small collaboration of CERN scientists are looking to pioneer international antimatter delivery. So what is antimatter, and why is studying it so important? According to quantum field theory, every fundamental particle has a corresponding antiparticle, with the same mass but an opposite electrical charge and reverse magnetic properties. However, you might have noticed that we don't see much of this antimatter in the universe around us. All the electrons we encounter are negative, all the protons we come across are positive. Where are the positive anti-electrons or positrons? Where are the negative antiprotons? Where is this antimatter hiding? This is a question that has puzzled scientists for decades. Cosmologists and particle physicists believe that the universe was created with equal amounts of matter and antimatter, but somehow a small excess of matter over antimatter developed in the very early universe. The particles and their corresponding antiparticles then smashed into one another and annihilated to create photons, particles of light. In doing so, all the antimatter was destroyed, and we were left with a universe filled with light and a small amount of matter. That matter went on to create the stars, planets, and ultimately, us. Without the creation of that initial excess of matter over antimatter in the very early universe, we would not be here. Physicists suspect that there are hidden differences in how physics treats matter and antimatter that can explain why matter survived and antimatter all but disappeared. Physicists have already observed such discrepancies. By smashing protons together in machines like the LHC, they have been able to create huge amounts of matter particles and their corresponding antiparticles. They have then been able to observe that these partners sometimes behave slightly differently, for example decaying at slightly different rates to one another. However, the discrepancies between matter and antimatter discovered so far, and facilitated within the standard model, are many orders of magnitude too small to explain the modern state of our universe. We need to find more discrepancies between the behaviour of matter and antimatter. We need physics beyond the standard model. The base experiment at CERN aims to search for more discrepancies by exquisitely measuring the properties of antiprotons, such as their intrinsic magnetic moment, and then comparing these measurements with those taken with their matter counterpart, the common proton. If they can tease out any differences, perhaps we will be a step closer to understanding the processes that facilitated our very existence. Of course, if we want to study antimatter, we need to be able to create it, capture it, and store it. So how do we currently create antiprotons and capture them for study? As of now, the CERN Antimatter Factory is the only place in the world where scientists are able to create, store, and study antiprotons. To create antiprotons, a powerful proton beam from the CERN Proton Synchrotron, or PS, a precursor booster stage of the Large Hadron Collider, is smashed into a block of iridium metal. These collisions create a multitude of secondary particles, including lots of antiprotons. However, given the power of the PS, these antiprotons are produced with a range of high energies and spread out in many directions. These diverging antiprotons are focused by magnetic and electrical fields, but only a fraction of them have the right energy to be tamed into a beam that can be injected into the 188 meter in circumference AD, or antiproton decelerator. The job of the AD is to tame these unruly particles and turn them into a useful, tight, low energy beam of antiprotons for storage and ongoing study. Of course, CERN is best known for enormous accelerators that accelerate particle beams to incredibly high energies. But the antiproton decelerator does the exact opposite. It is designed to decelerate particles rather than accelerate them. The AD is a ring composed of bending and focusing magnets that keep the antiprotons on the same track, while strong electric fields slow them down. The spread in energy of the antiprotons and their deviations from the track is reduced. We say the beams are cooled. Antiprotons are subjected to several cycles of cooling and deceleration until they're slowed down to around 1/10 of the speed of light. However, these antiprotons are still moving incredibly fast and are tough to capture and study. As such, during the 2010s and early 2020s, a new 30-meter deceleration ring known as a LENA, the extra low energy antiproton decelerator, was coupled with the AD. The LENA synchrotron uses electric fields to reduce the antiproton energy even further, by a further factor of 50 to just 0.1 mega electron volts. A beam of electrons is then injected and merged with the antiproton beam. The antiprotons and electrons Coulomb scatter and exchange momentum. As the particles move into thermodynamic equilibrium, energy flows from the antiprotons to the electrons, and the antiprotons slow down further. Once the antiprotons have slowed sufficiently, the light negative electrons can be deflected away with electromagnetic fields. This process is known as electron cooling and reduces the energy of the antiprotons to hundreds of killer electron volts. The antiprotons are now travelling slowly enough to be shipped to precision antiproton experiments for capture, storage, and long-term study. So how are antiprotons stored? After all, if they ever touch the sides of a matter container, they'll annihilate with a proton in a common atom and disappear. It is fiendishly difficult, but the fact that the antiprotons have been slowed down means that we can grab them relatively efficiently. Currently, The AD and ELENA serve several experiments that are studying antimatter and its properties: Aegis, Alpha, Asakusa, G-bar, and the experiment that draws our focus today, BASE. ELENA directs its cooled antiprotons along connecting lines into precision experiments such as BASE, which capture the slower moving antiprotons in cages of electromagnetic fields known as penning traps, held under high vacuum. A penning trap consists of the superposition of a strong and extremely homogeneous axial magnetic field with an electric quadrupole field. The electric field is configured so that negative antiprotons drifting along the z-axis, the axial direction, are reflected by a repulsive potential at the negative end cap electrodes, and therefore oscillate back and forth along the z-axis. However, in the vertical plane, the x and y directions, the electric field cannot constrain these antiprotons. In fact, it pushes the negative antiproton particles towards a positive ring electrode. The strong magnetic field directed in the z direction causes a radial confinement towards its axis and stops the particles drifting too far away from the axis and ever hitting that ring electrode. The result is that the antiproton remains trapped and perpetually oscillating in a small three-dimensional vacuum. Within the trap, the antiprotons display a complicated oscillatory motion. They wobble up and down in simple harmonic motion in the z direction. This is known as axial motion, but also oscillate around the axis of the magnetic field lines in the xy plane. This is known as cyclotron motion. The combination of the electric and magnetic forces also causes the antiproton to slowly orbit the center of the trap, a motion known as magnetron motion. The velocity of the trapped antiprotons is now reduced to a few millionths of the speed of light by additional cooling techniques, and once the unruly antiprotons are virtually at a standstill, further study can begin. The BASE experiment can contain antiprotons for more than a year, an incredibly impressive feat, which allows it to continue taking measurements of the properties of antiprotons, even when the PS is shut down and no more antiprotons are being produced. So we now understand how antiprotons are created, slowed, captured, and stored. But what measurements does the BASE collaboration want to perform with these antiprotons? Understanding these measurements is the key to understanding why BASE is so keen to move antimatter out of CERN's antimatter facility. BASE specialises in studying the fundamental properties of antiprotons, such as their intrinsic magnetic moment, with the highest possible precision. These values can then be compared to those of protons to tease out any discrepancies between these matter-antimatter siblings. So how do we measure the magnetic moment of an antiproton confined to a penning trap? A direct measurement of the magnetic moment requires the measurement of two frequencies associated with the motion of the antiproton in the trap: the cyclotron frequency and the Larmor frequency. As mentioned earlier, the cyclotron frequency is the number of revolutions per second that the antiproton makes around the magnetic field lines of the penning trap. Although I won't go into gory details, it turns out that the true cyclotron frequency of an oscillating antiproton in a penning trap can be determined by measuring its rate of modified cyclotron, axial, and magnetron oscillations within the trap. But how on earth can we measure the frequency of wobbling in multiple dimensions of a single antiproton under high vacuum in an electromagnetic trap? The key is a technique known as image current detection. When a negative antiproton approaches the walls of a penning trap, an increasing positive image charge is induced in the wall and can be detected by nearby electrodes. As the antiproton moves away from the wall, this induced current decays away. So by placing monitoring electrodes around the edges of a penning trap and carefully monitoring the frequencies with which charges are induced in the walls in different directions, with simple Fourier frequency analysis, we can access the three oscillation rates of the antiproton and determine its cyclotron frequency. The Larmor frequency measures the precession rate of the magnetic moment of the antiproton about an external magnetic field. Think of the antiproton as a tiny magnet with its own magnetic moment. An external magnetic field exerts a torque on that magnetic moment, and causes it to precess about the external field axis, with an angular frequency known as the Larmor frequency. The Larmor frequency is determined by using a special penning trap configuration and adding an inhomogeneous magnetic bottle to the standard setup. The details are not particularly illuminating, but what follows is very important. Once we have the cyclotron and Larmor frequencies, we can determine the magnetic moment of the antiproton. The cyclotron frequency of the antiproton in a penning trap depends on the charge to mass ratio of the antiproton and the magnetic field of the trap, while the Larmor frequency depends on both of those quantities, but also crucially on the magnetic moment of the antiproton. So by taking the ratio between the Larmor and cyclotron frequencies of the antiprotons in a penning trap, we can extract the magnetic moment of the antiproton. This magnetic moment can then be compared to the known magnetic moment of the matter proton to tease out any differences. In June 2014, the BASE collaboration reported the first direct high-precision measurement of the proton magnetic moment with a fractional precision of 3.3 parts per billion. And in 2017, BASE showed that the magnetic moments of the proton and antiproton are identical, apart from their opposite signs, within the experimental uncertainty of 1 part per million, an exquisite level of precision. So, if BASE is producing world-leading measurements at the CERN Antimatter facility, why are they devoting so much time to developing BASE STEP, a sub-project to transport their precious cargo of antiprotons to other labs around the world? Why are they looking to create an antimatter delivery service? Shouldn't they be focusing solely on their cutting-edge experiment and results? Well, it turns out that's exactly what they're doing. Developing the ability to transport antimatter is not just scientific camaraderie or a wish to provide antimatter to facilities without particle colliders. Moving antimatter out of CERN's antimatter factory is the key to improving BASE's measurements even further. Up to the current date, BASE has been able to compare the magnetic moments of the antiproton and the proton with a precision of roughly 1 part per billion. However, they want to go further and compare the magnetic moments of these matter-antimatter twins to 1/10 or even 100th of a billion. They want to be hundreds of times more precise and tease out the tiniest deviations between the behaviour of matter and antimatter. However, at this insane level of precision, the BASE collaboration runs into a problem: the operating environment of the CERN Antimatter factory. In the previous section, we saw that to determine the magnetic moment of the antiproton in a penning trap, we had to take the ratio of 2 equations, one related to the cyclotron frequency of the antiproton, and the other related to its Larmor frequency. However, this ratio only yields the magnetic moment of the antiproton if the magnetic field of the penning trap cancels in the ratio. In other words, the magnetic field has to be the same in both equations. We have to have used the same magnetic field to take both measurements. If the magnetic field is not the same, we introduce an ugly systematic uncertainty into our experimental procedure and cancellation that we have to account for. It turns out that the accelerator equipment in the antiproton decelerator hall at CERN generates pernicious magnetic field fluctuations when it is ramped up and down. These fluctuations impact the carefully calibrated magnetic environment inside the BASE experiment and stop BASE from increasing the precision of their magnetic moment measurements any further. If BASE wants to probe the discrepancies between protons and antiprotons even more carefully, they need to move their precious antiprotons out of the CERN Antimatter factory and into a dedicated laboratory with an extremely calm magnetic environment. In short, the production of antimatter requires a dedicated, expensive, and powerful particle collider, but the exquisite study of antimatter requires separation from that collider and the tumultuous magnetic environment it produces. As such, BASE physicists would like to transport antiprotons from their creation point at CERN Geneva to BASE experiments in Hanover and Mainz in Germany. These journeys will require the stable transport of antimatter over hundreds of kilometers and the lion's share of 10 hours. This is a feat which has never been accomplished before. Okay, so we now understand the motivations of the BASE collaboration in producing a long-range antimatter transportation system. But how can this Herculean task be achieved? How can we produce a containment system stable enough that antiparticles won't drift into any part of the container across the duration of a bumpy, undulating road journey? It is no small feat. In integrated stationary experiments like BASE, antimatter is stored in carefully monitored penning traps. The powerful magnetic fields of those traps are created by superconducting magnets cooled by liquid helium to almost absolute zero, and the electric fields and monitoring electrodes of those traps are powered from the local electrical grid. We can't just rip all this out of the wall and transport BASE to another location. This is where the BASE collaboration sub-project, BASE STEP, comes in. BASE STEP is an apparatus designed to store and transport antimatter. The device is 5 times smaller than the BASE experiment and can fit through generic laboratory doors. It weighs around 1,000 kilograms, meaning that it can be moved by cranes installed in the CERN Antimatter factory through existing exits and loaded onto a freight truck. Even though it weighs a literal ton, BASE STEP is by far the most compact system ever devised for trapping, storing and studying antimatter. BASE STEP will accept antiprotons from the ELENA decelerator into a number of penning traps. The BASE STEP device is essentially a mobile penning trap under high vacuum and consists of a superconducting magnet to generate a strong 1 Tesla magnetic field, cryogenic cooling to keep the magnet superconducting, and power reserves for the cooling and monitoring systems. The most difficult part of this operation is transporting an operational 1 Tesla superconducting magnet over huge distances by road. Superconducting magnets are usually shipped hot and current free. Here, to transport antimatter, we need a superconducting magnet to remain just above absolute zero and operational without access to grid power or huge stationary liquid helium tanks for extended periods of time. A 1,000 kilometer road journey from Geneva to Hanover takes 10 hours under optimal traffic conditions. When BASE STEP is connected in the CERN Antimatter factory, it is connected to external liquid helium and grid power supplies for cooling, operation and monitoring. However, to allow BASE STEP to be disconnected and moved, the apparatus contains internal power sources and a 30-litre liquid helium buffer tank. As such, BASE STEP can be disconnected from external power and liquid helium supplies for around 8 hours, without the superconducting magnet losing its superconductance and the penning trap degrading. This allows sufficient time for BASE STEP to be disconnected, moved onto a vehicle and transported short distances. And these distances can be extended if the vehicle carries appropriate liquid helium and power supplies. The superconducting magnet also needs to be shielded from mechanical shocks during road transport. As such, BASE STEP is carefully designed with a series of mechanical supports and damping mechanisms that can withstand and negate accelerations of 1g in all directions. The BASE STEP superconducting magnet produces a magnetic field of 1 Tesla. This is thousands of times higher than the magnetic field of the Earth, and comparable to those used in medical MRI machines. As such, the entire BASE STEP device is surrounded by a carbon and steel vacuum chamber, which reduces stray fields outside the box to a few millitesla, comparable to the field you experience when riding a bullet train. So when it comes to the safe and efficient transport of antiprotons, BASE STEP seems to have all the bases covered. Okay, so BASE STEP is incredibly cool, but does it actually work? And what's the current status? Well, 2 weeks ago, BASE scientists and engineers took a huge step towards demonstrating the viability of BASE STEP and the long-range transportation of antimatter. Base scientists and engineers loaded base step's penning traps with a cloud of 70 protons before disconnecting base step from the CERN Antimatter factory facility, moving it by crane onto a waiting truck, and transporting the cloud of 70 protons in the truck across the CERN site. This was the very first time in history that loose particles have been transported in a reusable trap that scientists can then open in a new location and use to transfer specific particles into another experiment. The protons were trapped, transported, and contained successfully. Of course, this initial test was performed with unbonded positive proton particles before base step is hooked up fully to ELENA and able to accept precious antiprotons. However, this demonstration was a monumental breakthrough, as containing antiprotons will only require a couple of tweaks to the system. Firstly, the polarity of the fields in the penning trap will simply need to be reversed to contain negative antiprotons instead of positive protons. In addition, the quality of the vacuum inside base step will need to be improved to ensure that our precious antiprotons do not collide with stray air molecules, annihilate, and be lost. Despite the fact that this initial test was performed with protons, it clearly demonstrated the feasibility of a mobile penning trap. This demonstration was a huge step forward towards an era of portable antimatter. So what more needs to be done to make an antiproton delivery service a reality? Well, base scientists intend to have base step ready for offline transport of antiprotons by the Large Hadron Collider's Long Shutdown 3 in July 2016. In order to do that, they need to clear several hurdles. They need to improve the quality of the vacuum inside base step to almost a perfect vacuum. They then need to hook base step up to ELENA and prove that the experiment can receive, capture, and transport antiprotons. In short, they need to repeat the feat of 2 weeks ago with antiprotons. But no showstoppers are perceived. During that step, planned for next year, base scientists intend to determine how many antiprotons can be stored and transported effectively inside base step. Experiments like BASE only use a few antiprotons to make precision measurements, but other antimatter experiments like PUMA destroy antiprotons during their studies and require far more. As such, the usefulness of base step as a delivery vehicle will in part be dependent on the quantity of antimatter it can store, carry, and deliver. Base scientists will also determine how long antiprotons can be contained in the trap without external power and liquid helium supplies. These measurements will constrain the range of any antiproton deliveries. In order to facilitate the transport of antiprotons over thousands of kilometers to external facilities in Germany or even further afield, base scientists also need to consider how external liquid helium and power supplies can be safely integrated into a long-range freight lorry. Currently, the main stumbling block for long-range antiproton transport is that the superconducting magnet must be kept below a frigid temperature of 8.2 Kelvin. When base step is disconnected from external liquid helium sources, the 30-litre backup tank of liquid helium rapidly runs out. The magnet warps, the penning trap collapses, and the precious cargo of antimatter annihilates against the walls. For these longer trips, base step will need access to a significant liquid helium supply, plus contingencies for delays caused by traffic jams. Just like a commercial plane, it will need to be overfueled. As such, huge liquid helium tanks and external power supplies will need to be integrated into dedicated transport vehicles. Of course, as a final step, base scientists will also need to develop an injection system and show that antiprotons can not only be transported effectively, but also effectively and efficiently decanted into a receiving experiment. These receiving experiments must be able to connect to base step under high vacuum and not allow any matter air to penetrate the seal between the two. As such, a series of ultra high quality adapters and connectors must be developed. There is much work still to be done, but it seems that antimatter transportation is, in principle, highly feasible, and that the creation of an antiproton delivery service from CERN to experiments around the world is just around the corner. The creation of antimatter requires energy, power, violence. However, the considered and exquisite study of that antimatter requires the very opposite, a separation from that chaotic maelstrom, serenity, calm. Base step scientists have demonstrated that antimatter production, capture, and long-range transportation is, in principle, highly feasible, and have taken the first steps towards an age of portable antimatter. Unlike the plots of science fiction movies, their goal is not to sow destruction or corner a commodity, but to facilitate a comparison between matter and antimatter so incredibly precise that it could open pathways to addressing the most important question of all. Why are we here? I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.